So today's lecture will be about the stack segment and how we can preserve registers across function calls. So let me start first with the stack segment. Now, why do we need a segment? Why do we need a stack segment? This stack in memory. So this stack segment will exist in memory. So why do we need this stack segment in memory? Now, suppose that you have any answer and any idea why do we need to have a segment in memory specifically for functions? Any idea about this?
I remember an idea because of recursive. We need the memory. Yeah.
True. Yes. For recursive functions, yes, we need to have a stack segment in memory. But we also need it for other simple functions. Yeah, even if we don't really have recursion, we also need a stack segment. Okay, if I have a function, now remember that the return address is stored in register RA. Remember register RA, the return address register? What does it store? The return address register.
RA.
Yes. So what does it contain, this register?
Contain the return address when a function is called. Contain the return address so it knows where to go back to the main code.
To the caller function, yes, correct.
Yeah.
Now, what is the number of register RA? Which register?
31.
Yes, thank you. So the jump and link instruction is going to store the return address in register 31. And the jump register is going to return back to the caller by jumping to the address which is stored in register 31. I talked about this in my last lecture. Okay, so what about if you have nested function calls? Yani if I have مثلا function f calling function g and function g calling function h, so we have nested function calls. What will happen to the return address? So every time you have a function calling another function, the return address is going to change, because when you execute the jump and link instruction, register 31 is going to change. The return address in this register is going to change. Right? Correct?
Yes.
Yes.
So what should we do about it?
Every return address refers to the next function until the last one gives the result.
Well, the return address contains the address where we would like to return.
Yeah, I return in another function.
So I would like to return back to the caller where the call was initiated. So if I make a function call, when I execute the jump and link instruction, I'm going to lose the return address in register 31 because this register is going to change. So I'm going to change the value of register 31, correct? The value of this register is going to change. It's going to contain a new return address. So the old return address, when we have nested function calls, the old return address is gone.
So we should save it in another register before we
Well, if you save it in another register, we'll have a problem because other registers might be used for other purpose.
So we save it.
Okay, and the other registers themselves might be changed by the function. So what we need to do is that we need to save this return address in memory. And when we save it in memory, we save it on the stack. So this is why we need a stack segment to preserve registers. Okay, so let me go into the details of this. So back here into my presentation. So in memory, every program has to have at least 3 segments as a minimum. It has to have a text segment. So the text segment here is what we call the code segment. So this segment will exist at certain memory addresses in memory. It contains the machine instructions. So when you translate these instructions from assembly into binary, these are the machine instructions. So these instructions will exist in the text segment. So the program counter contains the address. It's pointing to these instructions in memory. Okay, and we are going to fetch and execute these instructions that exist in the text segment. The data segment is divided into 2 parts. We have the static area and we have the heap area, which is the dynamic area. So we can allocate memory dynamically at runtime. The static area, it means that the size of this area does not change at runtime. The assembler is going to allocate data inside the static area, and the data will be loaded at the beginning of the program, and it will remain in the static area throughout the execution of the program. So this is why it's called static, because it does not change, and the allocation is done by the assembler. Whereas the dynamic area, this is going to grow. Okay, so you can allocate memory dynamically at runtime, okay, inside the heap area. On top, we have the stack segment. You can see here on top, we have the stack segment. So this stack segment is shown in green. It appears on top of memory, and it grows downwards. Okay, so the stack is going to grow downwards toward the lower memory addresses. This stack segment is essential, okay, because it is needed by functions. So the functions are going to allocate memory inside the stack, and it's going to free the memory on the stack. Okay, so the stack is going to grow downwards. Okay, so when we would like to allocate memory, we are going to have a pointer that will point to the top of the stack. And by decrementing this pointer, this address, we allow the stack to grow. And then when I would like to free the memory on the stack, I'm going to increment my pointer. Okay, so we have a pointer that will point at the top of the stack. We call it the stack pointer. And this is a memory address. It will just contain the address of the top of the stack. And we can allow this stack to grow, and we can allow this stack to shrink. Okay, so we can free memory on the stack. So this stack segment is very important. It's implemented by software. So by just adjusting, okay, the stack pointer, you can allocate and free memory. And this is done completely under the control of the program. So the programmer can allocate and free memory on the stack. Okay, so this is the importance of this. I'm going to show you how we can use it in programming, and you will see the importance of the stack segment. So the stack segment is used by functions. Okay, for example, we can pass parameters on the stack. If you have too many parameters and we cannot really fit them in registers, then we can pass them on the stack. We can allocate space for local variables on the stack. For example, inside the function, you might have a function that has, let us say, many objects, arrays, structures, okay, and these cannot really fit in registers. You can allocate space for them on the stack. So these are local variables inside the function. So they exist when you call the function, and they will cease to exist when you return from the function. So we use the stack for the local variables that exist inside the function. So we allocate them dynamically on the stack, and we free the stack when we are done with this function. We can save registers across function calls. Now, all functions that exist in my program will need registers. Every function in a given program might use registers. And therefore, because you have many functions are using the same registers inside the CPU, there will be conflict. Okay, so the same registers have to be reused, okay, by different functions. And if these registers contain important data, then what we have to do is that we have to save their values, okay, in memory on this stack before we can modify them, before modifying them. We'll see how this can be done in programming. I will show you how we save registers. And finally, for implementing recursive functions. So when we have recursion, okay, we need the stack segment. Without the stack segment, we cannot implement recursive functions. I will also give you an example about the recursive function in this presentation. In order to implement the stack, now the stack itself is just a segment in memory. Okay, all what we need is just, we are going to implement it completely in software. Okay, so the hardware does not really care. The hardware just has memory, and you can use it in your program the way that you want. We need a stack pointer. So the stack pointer, which is called SP here, this is register 29. So we are going to reserve this register specifically for this stack. It contains the address of the top of the stack. So we know exactly where the stack ends in memory. So the stack is completely implemented in software by the programmer. Okay, so the programmer here can decide how much memory is allocated on the stack. Okay, so this is the stack pointer. Some programming languages only use the stack pointer. In our cases, we are going to use the stack pointer only, and this is sufficient. But sometimes in some more advanced programming languages, okay, they use two pointers, a stack pointer and a frame pointer. This is another pointer, okay, which is register number 30 that will point to a stack frame, especially when the size of the stack frame can vary, okay, depending on the function. So if you have really complex functions and the size of the stack frame is not a constant, okay, it can vary, then you need a second pointer, which is a frame pointer. So initially, when you start execution of a program, okay, before the program starts execution, the stack pointer is initialized. So when you start the execution of the program, you can look at the value of this register 29, the stack pointer. It already contains the address of the top of the stack. So this is initialized, this register is initialized just before the program execution starts. Okay, so before the program starts, look at the value of the stack pointer initially before executing the first instruction, and it is already pointing at the top of the stack. So if you look at this, the Mars tool, and you look at the value of the stack pointer, you will find that its initial value is this number. It's a memory address, okay? It is a memory address. So this is the initial value when you start the execution of your program. Now, of course, on a real system, the operating system is going to initialize the stack pointer before we start the execution of the first instruction in the program. Now, okay, let me talk about the stack frame. So I talked about the stack segment, and the stack segment can contain many stack frames. Stack frames are for functions. Every function needs a stack frame. So this is the meaning of a stack frame. It's allocated by a function. So every function can allocate its own stack frame. And when it's done, when we finish the execution of stack frame, when we finish the execution, sorry, of a function, the function is going to free its stack frame. It's called a stack frame. Okay. It is also called an activation frame. The same meaning. So it's an area of the stack. That's the meaning of a stack frame. And it is allocated by a function. Okay. Just before a function begins execution, if it needs memory on the stack, it's going to allocate a stack frame for itself. And when it finishes execution, just before returning back to its caller, it's going to free the stack frame. So we need the stack frame to save arguments. Yani, for example, you might need to save certain parameters that were passed, or if you have too many parameters, you need to have them in memory. So you save them inside the stack frame. If you would like to save registers, okay, for example, if a function needs certain registers that might be needed by the caller function, or it wants to preserve certain registers across function calls. So it's going to save registers. If it has local arrays or local, let us say, variables, if any, it can actually save them in memory on the stack. So each function will have its own stack frame. The size of this stack frame can vary from one function to another. Okay, so therefore the stack frame can differ, okay, depending, of course, on how much memory a function needs. So when you push, okay, a stack frame on the stack, you are going to adjust the stack pointer and sometimes the frame pointer. If you are using 2 pointers, you need to adjust both of them. If you are only using 1 pointer, in our examples, I'm going just to restrict it to just 1 pointer. So we're going to adjust the stack pointer, okay, when you push a stack frame. So you push a stack frame when you would like to allocate memory for a given function. And you pop the stack frame, okay, when you are, you pop the stack frame when you finish the execution of a given function. So if you would like to allocate the stack frame, you decrement the stack pointer to allocate, and you increment the stack pointer to free. Okay, so every function is responsible for its own stack frame. As an example, so this is the frame for the function f, which is shown in yellow. Notice that the stack pointer, how it points at the top of the stack. Notice the frame pointer, it points at the beginning of the frame. Notice that the stack is going to grow downwards toward the lower memory addresses. So this is why we decrement the stack pointer. We decrement it when I would like to allocate memory, okay, on the stack, when I would like to allocate a new stack frame. Suppose that function f would like to call function g. So when function f would like to call function g will allocate its own stack frame. And this stack frame will be allocated on top of the frame f. But here top is upside down because the stack is upside down, okay? So we lower the values of the stack pointer and the frame pointer, and this way we can allocate a frame for the function g. Okay, so remember that the stack here is upside down and it grows downwards. So this is why we decrement the value of the stack pointer and the frame pointer. Okay, so the size of the frame of g does not really have to be the same as the size of f. Each function can allocate whatever number of bytes that it needs. Okay, and now if g returns after finishing the execution of the g, then g is going to free its own frame and restore the old value of the stack and the frame pointer. The stack pointer and the frame pointer will be restored by g after it finishes its execution, just before returning back to its folder. Okay, so by restoring the value of these the stack pointer and the frame pointer, then they are pointing again, okay, to the frame of the function f. Okay, is this clear? Now we are going to do it in programming, because all of this is done within programming. Okay, it's done by the software. Now, inside the frame, it depends on the function. Inside a single frame, you can actually have, let us say, the local stack variables. You can have saved registers. You can have arguments, okay, which are for nested function calls. So you can actually have many things inside the stack frame. Okay, so you can actually store many things inside one frame, okay, according to what the function needs. Okay, so we understand the meaning of a stack frame. Let us see how we can implement everything in software. Let us see how we write the program in assembly. In fact, if you really would like to understand what the compiler is doing, the compiler is generating the instructions for allocating these stack frames and also freeing them just before returning back to the coder. So the compiler is doing this automatically for us. When it's translating a program from high level to assembly, it does this automatically for us. But since we are programming directly in assembly, we have to do it ourselves. So we understand the details. okay, how the translation is done from high level to low level, okay, and we understand the meaning of this important segment. Now notice that because the function calls and returns appear, okay, in last, so basically the stack itself is allocated in a way. This is why we need a stack, because you see that the function f calls function g, and when the function g returns, okay, is going to free its stack frame. So basically it's last in, first out. Okay, last in is first out. So this is why it's a stack. Okay, so the allocation and the freeing of memory is done in last in, first out, and this is why it is a stack. Okay. You can also have function g calling function h. So therefore you are going to push the stack of h on top of g. And when function h returns, you free h. And when function g returns, it will free its own stack frame. And you go back to the stack frame of the function f. Right. So let me talk about a leave function. A leave function is a function that does its work without calling any function. Okay, this is why it's called a leave. So it does not really initiate any function call. Okay. So you can think about function calls and returns like a tree. You can actually have a tree of function calls inside your program. It looks like a tree. Now, when you reach a function and this function does not initiate any call to any other function, we call it a leave function. So you can execute the function, it does its work, and it returns without making a call to any other function. We have seen an example in my last presentation about the swap function and the function to lower. These were very simple functions. And these functions were leave functions. Why? Because they did not really call any other function. Okay, and this is why they are called leave functions. So a leave function can freely modify some registers. It can modify its argument registers. So the coder is going to pass the arguments and these argument registers. So the function is free to modify these registers. It's free to modify V0 and V1 to return results in these two value registers. Okay, if it wants to return results, it's free to modify these registers. And it's free to modify the temporary registers. In fact, any function is free to modify these registers. So these registers can be used by any function in a given program. Okay, so you can modify. So any function can modify them without saving their old values. There is no need to save their old values. And a leave function can be written without the need of a stack frame. You don't even have to allocate, so there is no need for a stack frame if you have a leave function, which is very simple. So in the case of the swap or the function to lower, we did not allocate a stack frame. There was no need for this stack frame because it can do its work using only registers if it's a very simple function. And remember that registers are the fastest memory elements. So there is no need to access memory in the case when you are dealing with a leave function. Now, if a leave function, okay, requires additional space for local variables, then it has to allocate a stack frame. And for example, you might have a leave function, but inside this leave function, you have an array, which is local to this function. So you only need it inside this function, and once this function finishes, then you no longer need the array. You don't really have to allocate the array on the heap. You can allocate on the stack. You can allocate a stack frame. So the leave function, even though it's a leave function, it can still allocate the stack frame if it has, let us say, a local array or a data structure that it needs only while executing this function. And once you are done, you can free the space you can free the entire stack frame, including the local array. Okay. So this is the meaning of a leave function. On the other hand, a non-leave function, it's a function that calls other functions. So if a function calls other functions, we call it non-leave. Yani it cannot do its work on its own. It needs to call another function to do something for it. Okay. That's a non-leaf function. In programming languages, of course, we call libraries. We call library functions. Okay, so these libraries actually were created since the 1960s. Okay, for more than 60 years ago, people actually have invented libraries and software libraries. Why do they have libraries? So that the programmer does not really have to write everything. Okay, so that you can actually reuse the code which is written by other programmers. Okay, so that's really the idea of libraries. You have actually many functions inside these libraries. Okay, and therefore you can actually reuse these functions by calling these functions. So a non-leaf function cannot do its work on its own. It has to call another function. If it's going to call another function, now the other function does not have to be in a library. I just mentioned the example of a library. It can be also a function in your program. Yeah, and you might call a function that exists as part of your program. In this case, okay, the non-leaf function must allocate a stack frame. It must allocate a stack frame. Why? Because if it's going to call another function, it's going to use the jump and link instruction in MIPS architecture. It has to use jump and link to call another function. And if it uses jump and link is going to modify register 31, the return address register. Okay, and if it modifies register 31, the old value of register 31 is gone. Okay, so therefore we have lost the value of register 31. So for this reason, the non-leaf function has to save the old its own return address. Okay, so suppose that function f would like to call function g. So now function f is a non-leaf function because it's going to call function g, right? And before calling function g, function f has to save its own return address because it wants to return back to its caller when the function f is done. So before making the call to function g, function f, it has to save its own return address. It cannot really use another register, okay, to save the return address. It has to save the return address in memory on the stack. So therefore, it has to allocate a stack frame at least to save its own return address. Right, to allocate the stack frame, the function has to allocate, suppose we would like to allocate the stack frame of n bytes. To do this, you need an instruction that will decrement the stack pointer by n. That's it. It will be a subtract instruction that will decrement the value of the stack pointer by n. By decrementing it by n bytes, we have allocated a stack frame of n bytes. You can, of course, the function has to decide how many bytes to allocate on the stack. Okay, as a minimum, it should be 4 bytes if you'd like to save only the return address. But if it wants to save other registers and would like to use the stack frame for other purposes, then it has to allocate more bytes. Okay, so you can allocate n bytes by just decrementing the stack pointer. That's how it is done. In our examples, we are going to focus only on the stack pointer. We are not going to use the frame pointer, so I'm not going to show the frame pointer. Okay, so the stack pointer is sufficient. We are going to keep the examples very simple. So we're going to decrement only the stack pointer. Now this n here must be multiple of 4 bytes because when you would like to preserve registers, the register itself is 4 bytes. So therefore the stack will be aligned in memory and its addresses will be multiple of 4. And we don't allocate 3 bytes or 2 bytes. No, we allocate 4, 8, 12, and so on. So this n must be multiple of 4. Okay. Now, as a minimum, if you have a non-leaf function, you must save the return address before making the function call. Because once you make the function call, the value of the return address has changed. The jump and link is going to modify register RA. You can also save other registers, for example, S0 to S7. Now, any function that wants to modify these registers has to preserve their values across a function call. So if a function wants to modify these registers, it has to save them in its stack frame before modifying them. This is the convention which is used by the MIPS architecture. Now, in order for the software to work, okay, now you might be writing a function and you would like to call a function that exists in the library, and this function is written by another programmer. There must be an agreement inside the software. I write my function, I would like to call your function, which is written in, for example, you have it in the library. I'm going to pass the arguments in these registers, A0, A1, etc. I'm going to return the values in these registers, V0, because the software is written in this way. All the functions are written exactly the same way. They use exactly the same convention. If I'm going to use S0 to S7, I must, as a function, I must save their values, okay, in my stack frame before modifying them. Because other functions, okay, have probably put some values in these registers. And therefore, I cannot modify these registers before saving their values on the stack. We can also allocate space for local variables, okay, if needed. You can also allocate more space in the stack frame. Now, let me show you, this is all just talking. Okay, let me show you some concrete examples how we can do all of this. So now, before I show you concrete examples, I need to mention here the steps. So if you would like to make a function call, make sure that before you make the function call that register RA is saved. Make sure to save before making the function call. And in order to do this, you have to save it in your own stack frame. So you have to allocate stack frame for your function and then save the RA register. Before making function call, make sure to pass the arguments in these registers, A0 to A3. If you have more than 4 arguments, then you have to pass them on the stack. Okay, because there is no really sufficient registers to save to pass all the arguments, then you have to pass the additional arguments on the in memory on the stack. In our examples, we'll keep it simple. We're just going to use, we're not going to have more than 4. Some architectures allocate more than 4 registers for arguments. They can go up to 8, for example, 8 registers, allowing you to also to pass more parameters in registers because it's faster than passing them in memory. Okay, you can pass the additional arguments, okay, in memory on the stack if needed, if you have more. And then use the jump and link instruction. So this is how you make a function call. Once you make the jump and link instruction, you have transferred the control to another function. You have initiated the function call. Okay. Now the jump and link is going to modify RA automatically. Okay, because it has to save the return address. Now, once you have finished the execution of a function, you have to do the following. You have to place the results in V0 and V1. If you have only one result, you place it in V0. If you have 2 results, you place it in V1. If you have more, you have to use memory. Sometimes if you have an array, you can actually have your result in memory inside the array. Okay, maybe if you are modifying an array in memory. So that's the first thing you have to do, place the results in V0 and V1. Restore all the registers that were saved upon the function entry. So if you have saved certain registers, restore their values. Load them from memory. Load them from the stack frame. They are in the stack frame, load them. And then free the stack frame. How do we free the stack frame? Increment SP. You have allocated n bytes. So free these n bytes because you have to restore the value of the stack pointer so that it points to the frame of the parent function, the function that initiated the call. Okay, so you have to free the stack frame and make sure to the last instruction is to return back to the caller. Jump register RA, return back to the caller. So these are the instructions. These are the steps. Okay, these are the steps to return from the function. Now let me talk something about the preserving registers. In the case of the MIPS architecture, the MIPS architecture, any architecture, it has to have a convention for passing arguments and returning results. Okay, let us see what should be preserved and what need not be preserved according to the MIPS architecture. If you have, for example, okay, register RA, the return address, this must be preserved. Okay, if you don't preserve it, you will lose the return address. Then the function does not really know where to return. So must be preserved. Okay, this is the return address. The argument registers need not be preserved. A function is free to modify its own arguments. The caller is going to pass the arguments in these registers, but once the call is done and you are inside the function is free to modify its own arguments. The stack pointer must be preserved. The stack pointer must be preserved. Why? Because when you allocate a stack frame inside the function, and just before returning, you have to free the stack frame, and you have to have the stack frame pointing at the top of the caller stack, of the caller stack frame. So therefore, you have to restore the value of the stack frame. Sorry, you have to restore the value of the stack pointer to point at the frame of the caller function. Okay. The value registers need not be preserved. Any function can place any number inside these, it can modify these two value registers, and there is no need to preserve their values because you are returning results. Okay. The saved registers, in addition to the frame pointer, if you are going to use them, they must be saved. Before you modify them, you save their values, their old values, and then you can modify them inside a function. Just before returning back to the caller, you have to restore their old values by loading them from the stack just before returning back to the caller. The temporary registers need not be preserved. Any function is free to modify these temporary registers without saving their values on the stack. Anything above the stack pointer must be preserved. Okay, so these are the frames of the parent functions. These must be preserved. The function is not allowed to modify the stack frames of its parents. Okay, so anything above the stack pointer is preserved. Anything which is below the stack pointer is free and it can be allocated. Okay, because remember that the stack grows downwards toward the lower memory addresses. So anything below the stack pointer is free, can be allocated, but anything above it, it already has been allocated, okay, by the parent functions, and therefore it cannot be modified. It has to be preserved. Now the caller is going to save register RA, okay, before making the function call. So which function is responsible, okay, of preserving the return address? It's the caller function. Okay. However, a callee function must preserve, okay, the stack pointer, the saved registers, and the frame pointer if needed. Okay, so this is the responsibility of the callee function. So there is a distribution of responsibility between the caller and the callee. Okay, so yes, Mushtaba, you have a question?
I didn't get what does the word preserve mean?
Saving the value of the register on the stack and restoring its value just before returning back to the caller. So preserving means saving the old value, because there is a value which is needed, okay, inside this register. So you might actually have more than one function that want to use the same register. So one function should not modify a register before saving its old value. So this applies to the stack pointer to the saved registers as 0 to S7. It also applies to register RA, also to the frame pointer. These must be preserved. Whereas the temporary registers, you can freely modify them. Okay. Now, if needed, the caller can save the argument registers. Okay. However, the callee function is free to modify them. Maybe this will be clarified if I give you some examples. Things will be more clear. Here's an example on preserving registers. Okay, so suppose I have a function f. Now notice that this function, I'm writing a very simple function f. Now this function f has two arguments, integer a and integer b. Now whenever we have two arguments, the convention is to pass these arguments in which two registers? How do I pass these arguments?
A0 and A1.
Yes. So let me just use my pen tool here. I need to write something. So I'm going to use my pen tool. Just give me a second. Right. So let us write on top of this. Okay, so this will be A, which is going to be passed in register A0. You agree? And B has to be passed in register A1. Of course, the caller has to pass these arguments A and B in register A0 and A1. This is the convention, right? It cannot really pass them in any other register because the function expects its parameters to be in these registers. Otherwise, the software will not work. Okay, in order to make the software to work, the software is a huge. You might actually be using libraries, different functions, okay, and these can be written by different programmers. The functions are written in a way that the parameters have to be passed in these specific registers, A0 and A1. The result, notice that there is an integer here. This is the result, okay? The result must be returned in which register? Which
V0.
register? V0, yes. V0. There is only one result, V0. The MIPS architecture allows functions to even return two results. Okay, and the C programming language, they only return one result. But if you would like to return, let us say, a structure containing two values, you can even return them in V0 and V1. Right, so we're going to return it in V0. This is the convention. So this is what function f is supposed to do. Now function f is going to call function g twice. Notice that there is a call here to this function g. And this is a second call to the function g. So we are calling function g twice. Now this function g can exist in the same program or it can exist elsewhere. Okay. Now according to the MIPS architecture, then the parameters for the function g, notice that g itself has two parameters. These have also to be passed by the, so f is calling g. So now f is the caller and g is the callee function, right? So f has to pass the arguments for g and it's going to pass them in A0 and A1, the same argument registers, because every function has to receive its arguments in these argument registers. Now we have two calls. Which one do you think is going to be done first, the outer call or the inner call? Which one should we do?
The inner first.
The inner first, yes, because we need the value of the result of the g before we make the call to the outer. So before I call the outer function, so this inner function here, this inner call has to be done first. So we have to pass A and B, we have to pass them in A0 and A1. Already we have them in A0 and A1 because the function f received them in A0 and A1. So we make the call to this function g. The function g is going to return a result. The result is going to be returned in V0. Right? Because this is the convention. G is going to return the result in V0. But this V0, we have to assign it to A1. And this B, we have to assign it to A0. Because in the second call, I have to pass B in A0, and I have to pass the result of the first call, V0, I have to pass it in A1 to make the second call. And this function is going to return the result in V0. This will be the result of the second function call. Now what I have to do, I have to return the value of A of D in V0 before returning back to the caller. The problem here is that this function f is going to call function g. Now, if it wants to return, we need to return address. And if we make a function call, we are going to lose, the function f is going to lose its return address. Notice that the function f is a null-leaf function. Okay? The function f is a null-leaf function. Why? Because it's calling function g. And as a minimum, it has to save its own return address to be able to return back to its caller. Okay? Now, we don't really know what function g does, and we don't really care what function g, where function g exists. All what we have to do is that we have to call function g properly. Okay? So in order to do this, this is the translation of the function f. It looks simple, right? But this is the translation. So I'm writing the function f again on top. So this is my function f. Now, function f is expecting the arguments to be in A0 and A1. If they are passed in different registers, it's not going to work. So they must be passed in A0 and A1. And the result, the caller of the function f expects the result to be in V0. If it's returned in any other register, then the software will not work. Okay? So this is why the software has to be written properly. This is why we follow these conventions. We are going to allocate a stack frame to save 3 registers. So we're going to save the return address. In addition, we're going to save A and B. I will tell you why we're going to save A and B in a minute. So first, you have to figure out that which registers must be saved on the stack. In this example, we need to save 3 registers. I need to save A because we are going to modify, because the function g might modify A. The function g might modify B. Remember that here we are calling the function g. Okay, and you are passing A and B in A0 and A1. Now, any function is free to modify its own arguments. So I don't know what function g is doing. I have to expect the worst. Function f does not know what function g is going to do with these registers. So since the convention is that any function can modify A0, A1, its own arguments, then once we return from this function g, the values of A0 and A1 might have been modified. They could be modified, right, by the function g. And if this is the case, then we have lost the arguments A and B. So in order not to lose the arguments A and B, we're going to preserve their values, these arguments A and B. These were the arguments of the function f. We're going to save them in memory on the stack. Okay. So I'm going to allocate a stack frame that consists of 12 bytes. Notice that we add -12. We add -12 when we would like to allocate the stack frame, because remember that the stack grows downwards toward the lower memory addresses. So this frame will consist of 12 bytes. 12 bytes means that we can save 3 registers. So 3 times 4 bytes, each register is 4 bytes. So 3 times 4 is 12. So you have to decide, you as a programmer, you have to think that, okay, how many bytes do you need, okay, on the stack, for the stack frame? So after we have allocated the stack frame, you see that the allocation is done by just one instruction. Just one instruction that will allocate the stack frame. After that, we need to save. So we're going to use 3 store instructions to save the return address. Why? Because it's a non-leaf function. When I call the function g, when f calls a g, then f is going to lose its own return address. Okay. So this return address, okay, was stored by the caller of the function f. So the caller of the function f has placed the return address in register RA. We don't really want to lose this return address. F does not really want to lose this return address. So it has to save it. It has to save A0 and A1 because these registers might be modified by the function g. So we can save them at different places, okay, on top of this stack. So at 0SP, this will be the address of the RA. at 4 SP and 8 SP. So we have allocated 12 bytes to save these 3 registers. Okay. After that, we can call the function G. So this is jump and link G. This is my first call to the function G. That's my first call to the function G. Now, I don't know what function G is doing. The parameters have been passed properly. A and B are still in A0 and A1, right? So we passed them to the function G, and the call was made. Now, once we return, so function G is going to do something. I don't really care what function G does. All what I care is that I just made the call, and then after that, I'm going to receive a result from function G. Now, once we receive the result will be in V0, because the result which is returned by the function G will be in V0. So I know that function G is going to return its result in V0. So what I need to do is that I need to make the second call to the function G, this call, this outer call. Now I need to pass B in A0, and I need to pass V0 in A1. In order to make the second call, we have to pass the arguments to the function G, because the G expects its arguments to be in A0 and A1. So now, oops, I took too much time on this. I'm running out of time. I was not really observing my watch. Let us just finish this example, and that's it for today. So I'm going to load, okay, from 8 SP. Notice that 8 SP is what? It's B. Okay, so we're going to load into A0. I'm going to move V0 into A1 to pass the arguments and make my second call to the function G. That's the outer call. So we pass the arguments in A0 and A1, and we make the second call. Now, again, the second call is going to return the result in V0. So that will be D, it's V0. So what I need to do is that I need to load 4SP, which is what? 4SP will be A0. So we loaded here in this load instruction. So we load A into A0, and I add A0 plus V0, which is A plus D, and put the result in V0. So we have to return the result in V0. So the final result will be in V0. Load the return address at 0SP. That's the return address. Free the stack frame by adding 12, because we are located on top here. Here we have to free. So we have to restore the stack pointer and then jump to RA. That's returning back to the board.